So first, recall that if y is equals sine to the minus 1 of x, then we can rewrite this actually by inverse property as x is equals to the sine of y. And of course, y is going to be in the domain between minus pi half and pi half. Now, because of that, the domain of sine of minus 1 of x is going to be from minus 1 to 1. So essentially, this is the domain where we have a relationship of inverse function. Okay, the functions are 1 to 1. Now, thanks to that, we can use the fact that now we have an implicit function of y to take the derivative. Notice if we have x equals sine of y, coming from y equals sine to the minus 1 of x, then we can take the derivative on both sides, and notice that over here is going to be simple 1, and on the other side we're just taking the derivative of sine of y, which is really easy and we know, which is cosine of y. But remember, this is an implicit function, so we're multiplying by the chain rule. Every time that we take derivative of a function of y, we need to multiply by y prime or by the y dx. Okay, so once that we have this, we have that the y dx is going to be 1 over cosine of y. And at this point, we can solve for the y dx, getting back to what the y dx is going to be in terms of x. So what do I mean by that? Well, remember that we have a relationship between the cosine and the sine. And sine square of y plus cosine square of y is 1. And so I can write this derivative in terms of x. In what way? Well, I can write cosine of y as plus or minus the square root of 1 minus sine square of y. Okay? And why is this good? Well, remember that sine of y is x. So sine square of y is going to be x squared. Therefore, I can write cosine of y as plus or minus 1 minus x squared. Okay? Because y is restricted to the interval minus pi half to pi half, so this means in terms of the plane, notice that in terms of the plane, we're talking about the plane, the xy plane, pi half is over here, right? So pi half in terms of angles is over here. This is the 0 angle, and so minus pi half is over here. So we're talking about this situation. This is the angles that are being covered. Now, if you think about trigonometric functions, remember that we're parametrizing points as x and y, equals, or let me just use a different letter. We use this point here, and for coordinates, if we have t and s, the point ts is just going to be the cosine of the angle and the sine of the angle. Okay, so and in this situation, in particular, we're just working with t that is positive. Notice that t here is positive, and s, which is the axis here, is moving from negative to positive, but we care about this. T is the cosine, and t is, in this case, is going to be positive in there. Okay, so cosine of y is going to be positive, and therefore we can say, oh, okay, so we can pick the root that is positive. And so because we pick the positive branch, it turns out that the derivative with respect to y, the derivative of y with respect to x of sine minus 1 of x is just going to be 1 over 1 minus x squared. Notice this is a function of x, but the procedure came from doing an implicit derivative. So we can establish as a theorem that the derivative of sine to the minus 1 of x, or the arcsine, remember that this is arcsine, is 1 over 1 minus x squared for x between minus 1 and 1. Now, if we take a look at how the functions are related, notice that f of x equals sine to the minus 1 of x is defined between minus 1 and 1. And this is the function that is going in here for the sine to the minus 1 of x. Now, the function f prime, of course, is going to reflect that. And notice that if we take tangent lines over here, these tangent lines are all the time positive, positive, positive. We reach just positive slope here, and there is a small change here in the concavity, but that's it. It's positive all the time, so that way we know that the derivative is going to be positive always. Okay, and because we have this equation, then we're sure that we're going to have as asymptotes 1 and minus 1. Okay. Now let's make a couple more of examples using the fact that we know now the derivative of the sine inverse. So we're going to take sine to the minus 1 of x squared minus 1, and also we're going to consider cosine of sine to the minus 1 of x. Okay, so let's write this over here. So the first one is going to be sine to the minus 1 of x squared minus 1, and the second one cosine of sine to the minus 1. Notice that in both cases we're going to have a chain rule going on. And just a brief reminder here, if y is sine to the minus 1 of x, or arc sine, so any of the two ways of writing that, then the y dx is 1 over the square root of 1 minus x squared. So thanks to this, notice that we can calculate what the derivative of this is. The derivative with respect to x of sine to the minus 1 of x squared minus 1 is, I'm going to actually take the derivative of sine to the minus 1, which is 1 over 1 minus, and now I'm going to compose the function inside. So the function inside here is x squared minus 1, and that's going to be square. We're composing in what this function is. And now we're going to multiply by the derivative of the function inside, which is 2x, the derivative of x squared minus 1. And so this is pretty much the solution. Okay, so 2x over a square root of 1 minus a square minus 1, a square x squared minus 1 squared. Okay, so that's the solution for A. Now in the case of B, we have a similar situation, but now we have a chain rule as well. We have y equals cosine of sine to the minus 1 of x. So here I don't have to worry directly by the first derivative. The derivative of cosine is sine. So I get sine composed with sine to the minus 1 of x, because that's the function inside. The derivative of cosine is minus sine. And I compose with sine to the minus 1. Now, because this is a chain rule, then I multiply by the derivative of the function inside, which is 1 over 1 minus x squared. And now notice the inverse property of sine composed with sine to the minus 1. This is just going to be x. Remember that that's the property of sine and their inverse. So the end result is going to be minus x over 1 minus x squared. Now, a similar function that we can find in that way is the cosine function. You can pretty much follow the same type of derivation to obtain the derivative of cosine to the minus 1, or arc cosine. So I'm going to leave that for you to confirm, and I'm going to move on to tangent to the minus 1. Notice that we do exactly the same thing. We have y equals tangent to the minus 1 of x. Since we don't have a relationship that we can exploit in there, what we do is we use the inverse relationship. We set up x as tangent of y. And so that's going to give me a lot of information on the domain. First, I gotta know that y needs to be between minus pi half and pi half, which is the interval where we have an inverse. And so the domain of tangent to the minus 1 is actually going to be minus infinity to infinity, as we can see in this way, because tangent always go in the range from minus infinity to infinity, so the inverse is going to have that as domain. Okay. Now, starting from the point that we have x equals tangent of y, we do the same procedure to find the derivative. Notice y equals tangent to the minus 1 of x, so we have that x is tangent of y, and then we take derivative on both sides. Notice the derivative of x is 1, and the derivative of tangent is secant square. And because we took derivative with respect to y, then we're going to multiply by dy dx. This is just a chain rule. Now at this point we can solve for the y dx, and we're going to get that the y dx is going to be 1 over secant square of y. And then at this point, when we get this secant square of y, we want to try and get back to function in terms of tangent. So in that way we can go back to x. Okay. Turns out here is really easy. We have an identity that is going to help us out do that. We have the secant square is just 1 plus tangent square. So that means that because x is equals tangent of y, then secant square of y is going to be 1 plus x squared. Then if I substitute that in the expression for the y dx, I'm going to have the derivative of tangent to the minus 1 of x is 1 over 1 plus x squared. Now, remember that the graphs of the inverse tangent and the derivative are going to be very informative of the behavior. Notice if f of x is tangent to the minus 1, f prime is going to be 1 plus x squared, and the derivative at 0 is going to be 1. That's going to be the maximum value of the derivative, so we're going to have the maximum slope at x equals 0. You can notice that this function is always decreasing. It's always decreasing. And so when we're approaching infinity or minus infinity, this is going to approach 0 as an asymptote. And we can see that the behavior, the derivative is going to be somewhat like this. It's going to be like a belt that is going to flat out at infinity. Okay? And of course, that's going to be consistent with analyzing what is tangent to the minus 1 of x. And how this behaves as a tangent line to it. Notice that if we have over here slopes, all the slopes of the tangent lines to this black function, which is tangent to the minus 1, are always positive. So this is telling me, yeah, the function is always positive, and that's it. And the fact that this is a rational function with bigger polynomial down there tells me that it's going to 0 when x is going to infinity. Now, we can actually go ahead and do the same thing with the cotangent. So again, I'm going to leave cotangent to you since it's exactly the same procedure. Make sure to follow this step by step and use the right identities, but you can solve cotangent in the same way that you did tangent. So now let's go and jump for secant square. Sorry, for secant to the minus 1. In here, if y is equals secant to the minus 1 of x, we're going to do the same thing that we did before. We're going to establish x is equals secant of y. Because of the domain of the inverse, we need to have that y goes from 0 to pi. That's the domain where the secant is going to be a function 1 to 1 that is going to allow inverse. Now, the domain of the secant to the minus 1 then is going to be the x, so that x is bigger than 1. Okay? Remember that secant is 1 over cosine. So if cosine is between minus 1 and 1, it means the secant needs to be bigger than 1 or bigger than minus 1. And so that's in terms of range for the secant. So that means that in terms of the inverse is going to have as domain the x bigger than 1 or smaller than minus 1. Now we do exactly the same things in terms of derivatives. Notice y is equals secant to the minus 1 of x, and x is equals secant of y. And then taking derivative on both sides, that's going to produce the derivative of secant is secant by tangent. And so we're going to get that 1 is equals secant by tangent, right? The y dx, because we're taking derivative of a function of y. And then from that we can find out that the derivative, the y dx of our cosecant is 1 over secant of y tangent of y. But then we have to do the same thing that we did before. We need to transform this in terms of x. So now x is equals secant of y, so you can see that we clearly have a x here. So the only thing that we need to transform is going to be the tangent of y. But that's still easy because we have the identity that secant square of y is 1 plus tangent square of y. And so that means that the tangent of y is just the square root of secant square of y minus 1. Okay? So because of the fact that x is equals secant, then that's going to be the root plus or minus the square root of x squared minus 1. Okay? And so in this scenario, we need to examine and resolve what is going to be the root, the sign for the square root here. And that happens by definition of the secant. If x is bigger than 1, then we're going to have that y is between 0 and pi half. And so that means that the tangent is bigger than 0. Now, in this case, we can take the positive branch, y equals x squared minus 1. However, if we are when x is less than 1, then pi half, y is going to be between pi half and pi. And that turns out to be that y is less than 0. So we can take the negative branch. So what this means is that this is going to account for the fraction the derivative. And so instead of now just having secant of y equals x, I need to multiply by the sign in front. So two scenarios happen. And so if x is bigger than 1, we have 1 over x square root of x squared minus 1. But if x is less than 1, then we have minus 1 over x square root of x squared minus 1. And so we can now fold this together using the absolute value definition. And we're going to get that secant to the minus 1 is just 1 over absolute value of x times square root of x squared minus 1. And so now notice that sine, tangent, and secant are the base for this. And you're going to find out that there is going to be just a small change in sign if you're going for cosine, cotangent, or cosecant. Notice that that's the only difference, the sign. Okay? So you should be able to go ahead and do exactly the same procedure that we did for cosine, cotangent to the minus 1, and cosecant to the minus 1. So I encourage you to go and actually do it. Now to finalize this, let's do a couple more of examples, but right here we're going to evaluate actually some values. So consider f prime of 2 squared of 3, where f of x is going to be the function x times tangent to the minus 1 of x over 2. And we're going to find the equation of the tangent line to the graph g of x equals secant to the minus 1 of 2x at the point 1 pi over 3. Okay, so let's do that. So first thing, we want f prime of 2 squared of 3, where f of x is x tangent to the minus 1 of x over 2. And so notice that we have a product rule here. We have we take the derivative of f, we can have derivative of x, derivative of tangent. So we need to solve that. So f prime is going to be x derivative tangent to the minus 1 x half plus x times the derivative of this. Okay? And so the derivative of x is just 1. So we get 1 times tangent to the minus 1 of x half. And then in here, we have now the derivative of tangent, which we know is 1 over 1 plus x squared. But now we have composed with x half, so it's going to be x half squared. And then we got to multiply now by our chain rule, which is the derivative of x half, so 1 half. Okay? So this is now giving me the full product rule for this. Now on B, notice that we're working with secant to the minus 1 of 2x. And we want to do it at the point 1 pi over 3. Alright, so if y is equals secant to the minus 1 of 2x, then the y dx will be what? We do the formula for secant, which is this. Oh, but wait a minute, this is 2x. So instead, it's gotta be 2x x squared. And now we multiply by the chain rule, which is the derivative of 2x, which is 2. Okay, so end result 1 over x. Oh, and I forgot, because I'm composing with 2x, should have a 2x over here as well. So now I get the 2 out, get this x, get this 2 over here, and for x squared minus 1. And so I get to cancel this 2, and I get 1 over x for x squared minus 1. And that will be the derivative of secant to the minus 1 of 2x. Now, one of the things that we're doing is also we computing what the points are. So for example, in the first case, f of 2 squared of 3 f prime of that is just going to be compute that over here. So that will be tangent to the minus 1 of the square root of 3. And then plus square root of 3 over 1 plus square root of 3 square. And so you can always use your calculator to find these values. Tangent to the minus 1 of square root of 3. So in this case it's pi over 3, and plus square root of 3. And square root of 3 squared is 3, plus 1 is 4. So this is my end result in there. And on this side, I'm trying to plug in the point 1 pi over 3. So the real value of x is 1. So if I plug in 1, the y dx is x equals 1. I'm going to get 1 over, so value of 1, 4 minus 1. So 1 over square root of 3. And that pretty much will be the exercise in there.